Hello and welcome back. Hope you had a fantastic Easter. This is Tuesday's lecture for week 13. We're going to spend the rest of the semester talking about methods of proof. So chapter 4 is about direct and indirect methods, and chapter 5 is method of induction. So we're almost done, yay! We won't be using this method, which I guess you could call the very direct method of proof. At least I hope not. And many of the exercises that we're going to be doing in this chapter, and in fact in number theory in general, I would say, rely on properties of even, odd, and prime numbers. And so I'd like to review those definitions real quick. We say n is an even number if it's twice some integer, and n is odd if it's one more than that. And this is the formal way of writing that. And n is a prime number if it's not the product of two integers, both equal to 1. And so the way to write that formally, what I just said in words formally, is this existential statement that this is false, this statement is false. There exist some integers r and s such that their product is equal to some number that's not prime, where r and s is unequal to 1. I don't know. I confused myself when I said that. I think if we take the inverse of this statement, remember when you invert existential, you have a universal, so, and you have to negate the predicate. So in this case it would be, for all integers r and s, the product of r and s is equal to a prime number if r and s both equal to 1, are both equal to 1. So n is prime if it's not a product, is the same way as saying n is prime if it has two factors, one of which is not equal to 1. I don't know. In any case, this is the formal way of making that statement. So, one key thing to note is we need two factors, and one of them can't be equal to 1. All right. The way I got this statement from this statement is just remembering that when I negate an if statement, I get an and vice versa. I get an and with the opposite conclusion. Okay, let's do a pop quiz on whether a number is prime or not. Is 0 a prime number? Well, we go back to our definition of prime. Does it have two factors, one of which is not equal to 1? Well, it's got more than two factors. In fact, anything is a factor of 0, because 0 times anything is itself, and so it has an infinite number of factors, so it is not a prime number. We also say it's not a composite number, because it doesn't have a finite number of factors. And is 1 prime or composite? Well, in this case, it's a little bit more straightforward, because it doesn't have two factors where one of them is not equal to 1. In fact, they're both equal to 1 and 1, so that is not a prime number. And it's not a composite number either, because it doesn't have 3 or more factors. So it's neither prime nor composite. And finally, are any even numbers prime? The answer is yes, because 2 is an even number. Why do we know 2 is an even number? Because 1 is an integer and 2 times 1 is 2. Therefore 2 must be even. We see that all of the even numbers are whited out in this case. This is the sieve of Eratosthenes, if you're familiar with that, except for the number 2 itself, because it has two factors, one of which is not 1. So it's the number 2 is a prime number. And this came up in semi-current events recently. This is after Hurricane Sandy. Mayor Bloomberg ran for president, and he made this statement. Drivers in New York City who have license plates ending in an even number or the number 0 will be able to buy gas on such a date. So that implies that 0 is not an even number. But it also sort of implies that he didn't throw it in with the odd number, so it's probably not odd either. So the question is it even or odd? And the answer is it's even, because 0 is an integer, and twice 0 is equal to 0. That means that the number 0 must be even. Some people say it's even the most even, because you can just keep dividing it by 2 and you'll get an integer forever. Here's the Cliff Notes summary of the direct methods of proof. There are only 4 of them, and the first page is the easy page. We've done this basically in class already. If you write your universal statements in this conditional form, and our existential statements in this form, you'll notice that if I negate this, I get this, and vice versa. We prove an existential statement just by finding an example. They call it the method of construction in your textbook, but it's really just finding an example. And vice versa, we disprove a universal statement by finding a counterexample or showing that there's one case where it doesn't work. So to prove an existential, we find one example that does work. To disprove a universal, we find one example that doesn't work. Hopefully you'll agree that's kind of easy to keep straight. They're complementary problems. They're basically the same problem, I might even add, because if for some reason you find it difficult to find one example where this works, then you can just invert it. You could say, for all even n is not the sum of two primes, then all you need to do is find one example where it doesn't work. And then you see that you end up with exactly the same thing. So your book mentions that the method of construction involves two separate things, which are closely related. One is you just you pick a specific example and you show that it meets that requirement. For example, there exists an even n such that the n is the sum of two primes two different ways. And if you just start going through your n's, start with n equals 0, it doesn't work, n equals 2, let's see, 1 and 1, that doesn't work. So n equals 4, I have 1 and 3, but 1's not prime, so that's no good. N equals 6, 1 and 5, 1 isn't prime, so that's not good, even though 3 and 3 are both prime. 8 would be the next one. 8, I have, let's see, 1 and 7, no, that's no good. 2, 3, 3 and 5, that seems to be good, but that's all. I just have one way to do that. And then finally I get to 10, and I see that 10 is the sum of 3 and 7 and 5 and 5, and so that works. And this is the sort of notation that you'll be using in Cengage, where you have statement in brackets that make it true. This is basically the truth set for this statement. Or it'll be in domain and codomain form in this one. So this is a way of giving the recipe. You don't necessarily need to find a specific instance of R and S where this works, but it's relatively easy to demonstrate that this is twice the sum of 11R plus 9S. So all I do is I take this divided by 2, and then I know that if I take twice this number, I get 22R plus 18S by the associative property of multiplication. So this is a recipe for finding some specific values for R and S that will make this statement true. And to disprove a universal statement, we just have to find an example that does not work. So to disprove the statement for all a and b in the set of real numbers, if a squared is equal to b squared, then a is equal to b, all we need is one example. And a negative number comes to mind really quick. If I let a equal 1 and b equal minus 1, then if I square 1, I get 1. If I square minus 1, I get 1 also. That means the squares are the same, and yet they are not the same. So what I just did is I found an example where the conclusion was false, but the premise was true. If the premise is true and the conclusion is false, our if-then statement is false. So I've disproved this universal statement. Unfortunately, the vast majority of proofs in mathematics are not of this type. They're mostly proving universal statements. So so that means we have to do something a little bit more difficult. Now, if you'll go back to your methods of induction handout from early in the semester, you'll notice that one of them was generalization. And we talked about the method of exhaustion too. The method of exhaustion is still something we do, right? Especially with computers. When you have a finite set, you can explore every number in the set and prove that that it's either true or false for every number in the set. So it's possible, especially with a machine. But it's not typically done. But here's an example. For all n in the set of integers, if n is even and n is between 4 and 10, then n is the sum of two primes. So I have a pretty small set here. I have 4, 5, 6, 7, 8, 9, and 10 to consider. So 1, 2, 3, 4, 5, 6 different, I had to use my fingers to figure out all of the numbers that I need to go through. So using the notation from Cengage again, for n is equal to 4, if I look, is n the sum of two primes? Well, yes, 2 and 2, those are both prime numbers, so that works. The next n would be, oh, I see, I said that there were 5, but it's only 4, 6, 8, and 10. It's only 4. So the next even n would be 6, and that also works because 3 and 3 are 6, and those are both primes. And then 8 has 3 and 5, and 10 have 3 and 7. So we have shown that for all n and z, this is true for all n. Right? There's not a single n in the set of 4, 6, 8, and 10 where it's not true. So we've used the method of exhaustion to prove that universal statement is true. Hopefully we don't have to do many of those. The other one, the far more common one that you see in formal mathematical proofs, is generalization from the generic particular. And that terminology just means we pick some x that is any element in the set. In this case, it's an element in the set of integers. And we have to specify that it's a particular value of x. That way we can find the truth value of it. So for some generic but particular member of this set, let's show that this equation is true. And I took this from an exercise that maybe you've done, if you've seen The Mentalist or anything like that, where they'll say, okay, I want you to imagine a number. It can be any number. Go ahead and write it down, but don't let me know what it is. Okay, now add 5. Okay, got that? Now multiply it by 4. Now subtract 6. Okay, divide all that by 2. Now subtract twice your original number. And I'm going to guess. I'm going to guess what the result is. Even though I have no idea what your original number is, I'm going to guess that it's 7. Well, am I a mathematician or a mathemagician? Well, you can just do some elementary algebraic manipulation to discover that this actually turns out to simplifies to 7 because the x's cancel. So that's a way to prove that this statement is universally true for any value of n. I take a specific, a generic, particular value of x. And then this last one, 4, is basically not any different than 3. What we're going to do to disprove an existential, remember up here we said we can prove an existential just by finding one example. But to disprove an existential, that's not so easy. In fact, what we have to do is we have to prove the opposite. So to disprove this, first I invert it. So this is, there exists an n, which is an element of the positive prime integer such that n squared plus 3n plus 2 is prime. The opposite of this would be for all n in the set of positive integers, n squared plus 3n plus 2 is not prime. So to disprove this, I have to prove its opposite. So to prove this statement, I'm back and using the methods of number 3. I have to prove a universal statement. And I'm going to use generalization from the generic particular again. I'm going to choose 2 particular values of n. I know that I can factor this out to be n plus 1 and n plus 2. And these are both factors of n squared plus 3n plus 2. They're both integer factors of n plus 1 of n squared plus 3n plus 2. So I have 2 factors, and they're both not equal to 1 because it's the same n, so they both can't be equal to 1. Therefore, this is a prime number. Okay. And just a little takeaway box here. We can't negate and do the opposite because you can't disprove an existential or prove a universal with a single example. Speaking of examples, I have a couple, 4, that I'd like to do. It's on the whiteboard that you have access to from our class. The first one is, I'd like to prove that there is an integer n such that blah blah. So this looks like it is a existential. I want to prove an existential such that all this is prime. Okay, well, it's going back to our thing. To prove an existential, let's see, is it this? No, it's not that. Prove an existential. So I just need one example where it works. Probably you knew that already. So let me just, it says an integer, so I can start with n equals 0. Let's try 0. If I plug 0, I love things that multiplying by 0 because it's always 0. 2 times 0 is 0, 5 times 0 is 0. So 2n squared minus 5n plus 2 is equal to 0, is equal to 2, sorry, for n is equal to 0. Okay, did I find, is 2 prime? 2 is prime. Okay, so 2 is prime, 0 is an integer, so I found domain and codomain that makes this example true. So I've proven that there is such a thing. All we needed was one example. We have one example. Done. All right, next I'd like to disprove this statement for every integer p. So that means for all p, I probably should have gone back to black here. For all p, we'll use the Tarski notation again. If p is prime, then p squared minus 1 is even. Okay, this is disproving a universal. So what did we say? Let's see. To disprove a universal, we just need one example that does not work. Here we found an example that does. Here we need one example that doesn't. Oh, come on. Okay. So one example that doesn't work. Well, let's start with the first prime number I can think of, which is 2. Is 2 squared minus 1 even? 2 squared is 4, minus 1 is 3. Oh, that doesn't work. Right? 2 is prime, and yet p squared minus 1 is not even. Well, it didn't work. So this is one example that does not work. So we've disproven that for all prime numbers p squared minus 1 is even. Sorry. Right, so unfortunately that finishes the easy examples, and a majority of your homework problems fall into that category. I did include a couple where we have to use the method of generalization. So here's one where we need to prove that if one root of this is rational, then the other root is rational. So I'm going to pick a generic but particular value of root. So I'm going to let I'll call one root x1 and the other root x2, and I'll say that these are both elements of rational numbers. And notice it's given that b and c are also rational. I'm going to say there exists an x1 and x2 such that this product is equal to 0. Then I hope you'll agree that x1 and x2 are roots of this equation, right? If I let x equal to x1, then that means this term is equal to 0 and the product is equal to 0. Or if x is equal to x2, then this term is equal to 0, therefore the product is equal to 0. So we say that x1 and x2 are roots of this equation. And we know that our quadratic in standard form is this. It's also equal to 0. Now I'm just going to FOIL this out and compare my terms. So this gives me x squared, let's see, minus x times x1. And then x and minus x2, so minus x, x2. And last, minus x1 times minus x2 is plus x1 and x2. And further, I can write this like this. Just to make it look like this, I'm going to have a term in front that looks like minus x1 minus x2. That'll be my b times x. You notice I just factored an x out of these two terms. Okay, now for those to be equal, that means these are the roots, the constant terms. That has to be equal to c. And this term has to be equal to b. Okay, well, if I know that minus x1 minus x2 is equal to b, then I can solve that. For x2, and I get x2 is equal to minus b minus x1. Well, this x1 is rational. B is rational. It says so in the problem statement. So these are both rational numbers. And the sum or difference of rational numbers is itself rational. So x2, the second root, is also rational. And I can put a QED here because I've demonstrated that which was to be shown. Okay, finally, one last one. I want to disprove an existential. There is an n. That means I have this, such that if n is odd, d's are just terrible to write with this thing. Then n squared is even. Okay, well, to disprove, we'll go back to the presentation again. To disprove a existential, what we do is we invert it and we prove the opposite. So let's write that down. Where are we? Nope. Okay. That's good enough. Okay. All right, well, what is the opposite? The opposite is, for all n, n is odd, and remember the opposite of an if statement is an and statement, where I take the opposite of this. I would say n squared is not even, and another way of saying not even is odd. So I'll just write and n squared is odd. So now I go back to my definition of even and odd. Right? An odd number can be expressed like this: n equals 2k plus 1, where k is some integer. So let's try that. 2k plus 1. If I square it, let's see, foiling this out gives me 4k squared plus 2k, so that's 4k plus 1. Well, this is 4 times anything is itself even, because k is an integer, so k squared plus k is an integer. So this is twice some integer, some other integer. Wow. Let's call it j for fun. So now I forgot to bring down my 1. So that means n squared is equal to twice some other integer plus 1. Well, that's the definition of odd. So n squared is odd. So we've proven that the opposite is true. Therefore, our original statement, there exists an n such that if n is odd, then n squared is even, is false. I won't write that down, I just said it. Okay, well, if you have any questions, please don't hesitate to call or write, and I'll see you on Thursday. I should have said text or email. Take care.